If you have looked at any of the names of the muscles, you will have quickly discovered that their naming pattern is very complicated. And I think it would be quite useful in helping to understand which muscle is which if we understood where the names come from. So let's consider a little bit some of the different kinds of muscles and then try to figure out how the names have anything to do with that. If we look here at the different shapes of muscles, sometimes muscles are named based on shape. So we can have circular muscles, and the example here is orbicularis oris. And what this tells us about that muscle is the orbicularis part tells us that it orbits. So it's a circular muscle, it's orbiting something. And oris then tells us what it's orbiting, in this case, the mouth. So these are actually the muscles of the lips. And then we're now saying these are circular muscles that are orbiting through the lips, and so that's hopefully useful in helping to understand that particular muscle. We have different shapes of muscles here, and I'm not going to get into great detail on those necessarily. But pectoralis major is a convergent muscle, sartorius is a parallel, and those don't have as much necessarily to do with the name and understanding it, but just understand that muscle fibers are arranged in different patterns. And those different patterns have something to do with their functionality at least. Some other things that are involved in naming muscles, and this is perhaps more useful, is the location of the muscle. So if we're talking about the temporalis muscle, at this point hopefully you would remember that the temporal bone is the bone of the skull right above and underneath the ear. So if we know that's the temporal bone, the muscle directly on top of that would be the temporalis muscle. If we're talking about the frontal bone, the muscle over the top of that bone would be the frontalis muscle. So muscle location is often useful as well. Another example would be intercostal muscles. In this case, the intercostal would mean in between costals, so in between ribs. So muscle location is often something that's used in naming the muscle. Muscle shape is another common naming convention. A good example here is the deltoid muscle. This is the muscle on the outer shoulder, actually responsible for moving the upper arm. And its shape is a delta, or triangle shape. So in the world of math, a delta is a triangle, so here the name is describing its shape. The trapezius muscles form a trapezoid shape, so that's another good example of shape driving the name. Size is often a piece of this equation. So if you talk about a muscle that is a maximus, a minimus, those mean large or small. Longus would mean long, brevis would mean short. So if we talk about the gluteus maximus, we're talking about the region in which the muscle is found, the gluteal region, and we're talking about the size, in this case large. So gluteus maximus literally means large gluteus. And this is actually the largest single muscle in the body. So it is very aptly named. Gluteus minimus would be the smaller gluteal muscle. The direction that the muscles run is often used in the naming as well. Rectus abdominis is a fabulous example of this. Rectus would be referring to the direction moving in an erect or an up and down direction. Abdominis would be the region in which it's found. So this is the muscle that is capable of giving a person six-pack abs with the right amount of working. Transversus abdominis would be another muscle close to the rectus abdominis, but in this case running in a transverse direction. So this would be running left to right in the abdominal region. The number of origins, or number of starting points for the muscle, is also useful. Biceps brachii would have 2 pieces. Triceps would have 3. The quadriceps muscle in the upper leg would, as its name suggests, have 4 components. Where the attachment points are for the muscle are sometimes used in naming as well. My favorite example of this would be sternocleidomastoid. So just take that one piece at a time. Sterno would refer to sternum, cleido would refer to clavicles, and mastoid would refer to the mastoid process of the skull. So the sternocleidomastoid muscle is attached to the sternum, the clavicle, and the mastoid process. Muscle action is also a significant factor in naming muscles. So if we talk about flexor carpi radialis longus, flexor would refer to its function, it flexes. Carpi tells us what it flexes, in this case the carpals of the wrist. Radialis tells us where the muscle is running along the radius. And longus would describe its size, it's long. So it's a long muscle running along the radius that flexes the wrist. If a muscle were an extensor, that tells you that it's extending something. So the opposite of a flexor. Knowing all these different naming conventions is, as you are starting to hopefully appreciate, useful in figuring out what a muscle looks like, where to find it, and how to know you've got the right one. And as we've already demonstrated here, often we have multiples of these mixed together. So with our flexor carpi radialis longus, we included location, we included size, we included what it does, and we included where in the body to look for it. So hopefully understanding those particular naming criteria will help you better be able to figure out and understand these different muscles that you'll find in this chapter. Muscles work in association with bones to form levers, and levers are really the movements of your body to achieve work. So these levers, we could talk about your elbow, your wrist, your knees, something like that, can be one of two different types. They can either be a power lever or a speed lever. A power lever works at a mechanical advantage, meaning if you put in a certain amount of effort or input of force, you actually get out of it more than you put in. So the example here is the jack on a car. And every lever is going to have an input of load or effort. It's going to have an output of load, and it's going to have a fulcrum or a pivot point at some point in that process. So where the input is relative to the fulcrum and where that is relative to the output determines the effect. So the power lever here, if we put in 10 kilograms of effort, we can actually get 1,000 kilograms of output in this particular example because the fulcrum is much closer to the output than it is the input. The example of jacking up a car. To utilize a car jack to lift the car, and let's say the car weighs 2,000 pounds, you don't have to put 2,000 pounds of effort into the jack handle. You put perhaps 20 pounds of pressure on the jack handle, and that results in 2,000 pounds of output of force on the car. Now you don't jack up a car rapidly. The jack works slowly, a little bit at a time. So it's a slow system, but it is a mechanical advantage because you're getting far more out of the system than you're actually putting into it. So if it's a mechanical advantage, it's probably going to be a slower lever. But that also allows you to do things that you would never otherwise be able to do. Our second example here is a speed lever. Now a speed lever allows you to do things very quickly, but it works at a mechanical disadvantage. So in this case we have the fulcrum on one end, the output on the other, and the input of effort somewhere in the middle. So our example here is to put 50 kilograms of output, we had to input 100 kilograms. So that obviously is not efficient. Think about in this example shoveling rock. If you've ever had the opportunity to shovel rock or dirt or anything else heavy for that matter, you'll discover that you don't slowly insert the shovel into the pile of rock or dirt. It works to very quickly insert the shovel and then very quickly scoop it up and throw it. If you were to try to do this slowly, it just wouldn't work because you're working at a mechanical disadvantage. And the faster you do something at a mechanical disadvantage, the easier it is to do. So we're going to look at three different categories of levers, and they're all going to have something to do with a speed lever or a power lever. And we'll look at some different examples of those throughout the body. Our first example is a first-class lever. In this case, the fulcrum is somewhere in between the input and the output. And the more balanced it is, the more balanced the output is. An example would be a pair of scissors. So a pair of scissors has the pivot point, or the fulcrum, roughly in the middle, with the handles on one end where your input would go, and the blades of the scissors providing the output of force. So if you want to cut 20-pound paper, and the fulcrum is roughly in the middle of this system, you're going to put about 20 pounds of effort in to get 20 pounds of effort out. If the fulcrum were closer to the end of the blades, so in other words, longer handles and shorter blades, you would discover that it takes less effort than the 20 pounds of effort input to cut 20-pound paper. So position of the fulcrum within any particular lever determines its efficiency. In this case, the scissors were balanced, and there are some significant advantages to having a balanced system. An example of a first-class lever in the body would be the head sitting on the neck. The head is roughly balanced, and so if you want to tilt the head back, the muscles on the back of the neck are going to do that, but the head was roughly balanced on the neck, meaning the fulcrum was roughly in the middle. So the input of force coming from the backside is going to pull the front of the head up and backwards, and because the system was relatively balanced, it takes about the same amount of effort to tip the head backwards as it does to tip the head forwards. This works nicely because you want the head to go both ways, but you don't necessarily want it to be advantaged or prone to one particular direction over the other. A second-class lever has an input on one end, the fulcrum on the opposite end, and the output somewhere in the middle. The example here is a wheelbarrow. If you ever used a wheelbarrow before, you would understand that if you put 200 pounds of concrete blocks in that wheelbarrow, it does not take 200 pounds of input of effort to pick up the wheelbarrow and move it. That's the whole point of a wheelbarrow. If you put 200 pounds of load in it, and it required 200 pounds of effort to move it, what's the point of using the wheelbarrow in the first place? So you can move that 200 pounds of weight with perhaps an input of somewhere around 50 pounds of effort, because the pivot point is on the opposite end. This is a mechanical advantage. It's efficient. It's very helpful to have this. So in an area where you need to have a mechanical advantage, you need to have an output greater than your input. This is the kind of lever you want to have. The example here is your ankle. Your ankle is going to support and move the body when you move your foot. So if the input of effort is from the calf muscle on the back side of the foot, the load is in between that and your toes, the fulcrum then becomes the ball of the foot and the toes, then you have the wheelbarrow effect. You're putting effort in on one end, it's pivoting on the other, and loads in the middle. So if I weigh 241 pounds as of yesterday, how many pounds of force must my calf muscles exert to stand me up on my toes? The good news is they don't have to exert 241 pounds of pressure. If they did, they would tire quite quickly. So even the idea of walking, that sort of thing, is going to involve this process. So to move that 241 pounds of output, probably 50 to 75 pounds of input pressure is needed. And it turns out that the calf muscle is quite capable of producing that kind of input. And so this is a mechanical advantage. It doesn't take as much effort to walk as it would seem based on the amount of weight being moved. A third-class lever involves output at one end, fulcrum at the other, and input of force somewhere between the two. This is definitely going to be a speed lever situation here. So an example is a pair of tweezers. You can very quickly and very precisely utilize a pair of tweezers to pick up an object. But because the input of force is in between the fulcrum and the load, it is far from efficient. An example here would be the elbow. The elbow would be the pivot point or fulcrum. The input of effort would be the upper arm. The output of force would be the lower arm. So if you're flexing the arm, let's say you're lifting weights using a barbell system like we see here, you're going to have an input of force that has to be greater than the output of force in order to work. So this is what lifting weights in this fashion achieves by building muscle and why it's so effective. If that barbell weighs, let's say, 10 pounds, the biceps muscle of the upper arm might have to put 15 to 20 pounds of effort into it to move the 10 pounds because of the position of the pivot point. So this actually works the muscle much harder than perhaps like we would say the calf muscle would for its job. So you can do this quickly, you can do it precisely, but it is very inefficient. In this case, we were looking for speed and we were looking for precision. So the third class lever was definitely a mechanical advantage, or rather a mechanical disadvantage, speed lever situation. Hopefully this was useful in helping you to understand and appreciate muscles and what they're doing, and perhaps more importantly, where their names come from. And for me, understanding what their name means helps me remember the name and helps me find that particular muscle when I'm looking for it. Hopefully you have already started looking at the polka muscle game, although I've only received the proof of completion from about 2 of you, so the rest of you really need to get working on those things. But hopefully that will help you to appreciate those muscles more fully and identify them more accurately. So what I would like you to do for the rest of this chapter is to go through and look at the muscles. And I'll put a PowerPoint up here hopefully for you to look at, but you can just flip through the pages and look at the muscle list that I will post along with this video. And take that list and then go find those muscles and identify those muscles in the drawings so that you know where they are. And hopefully when you're seeing them again, you would be able to know exactly which muscle you were looking at. So hopefully this was all informative and helpful. Have a wonderful day, and I'll see you next time.